for hosting this. Thanks everybody for coming. This is really kind of a nice opportunity, it seems like, to bring together a considerable cross section of people from across a variety of disciplines. So I really like this seminar series and enjoy taking advantage of it through its recordings on YouTube and so forth. So today we're going to talk about title is How Does Glacier Ice Flow and Deform, which is meant to be kind of a general audience style topic. What we're really going to talk about is the rheology of the ice, and specifically how it deforms, the mechanisms by which it deforms, and some recent work that we've been doing to try to do a little bit of a better job of constraining all these various factors, calibrating parameters that go into ice flow models and so forth. Now, I'm just the one talking. All the work that I'm going to talk about is being led by members of my group, particularly two students, Joanna Milstein and Megan Oranganathan, as well as research scientist Brian Rheel in my group. So I'll try to highlight as we go their contributions to all this, but they're really the main folks. I'm just the person that pays the bills and tries to keep up with what they're doing. So start off with a general slide on Glacier Dynamics. Just as an overview for a broader audience, I consider Glacier Dynamics to be sort of the greatest hits of geophysics, which is to say that kind of a lot of the things that are in geophysics, and by geophysics, I mean now solid Earth geophysics, a lot of the interesting problems that exist in solid Earth geophysics also exist within Glacier Dynamics, but they occur at different timescales and they occur in locations that we're able to observe. So we have interesting rheology going on. We have interesting interactions between different types of rocks, so to speak, so ice flowing over the solid Earth and so forth, and deformation of beds. We have interactions between various systems, so the ice sheets and the broader climate system and so forth. But in a nutshell, kind of one of the things that excited me about glaciology at the very beginning is coming from solid Earth geophysics background, is that it's effectively geological processes that are playing out over human timescales in areas that we can observe very well. So, but moving on from that, kind of thinking about the field as a whole, we naturally want to address some overarching questions and so forth. And some of these questions that are listed up here, of course, are very obvious. We think broadly about how do ice sheets respond to climate change? How do they contribute to sea level rise and so forth? And then we also think about the other side of things, the flip side of the coin, and thinking about how do glaciers shape the solid Earth? Glaciers are a major agent of erosion and these boundary conditions and so forth. The connection between glaciers and the solid Earth is a key feature of understanding the shape of our Earth and the morphology of the surface. Now, the thing that we're concentrated on for the most part as a field, I would say the central challenge of glaciology, of course, is to make testable and ultimately reliable predictions of the response of glaciers and ice sheets to climate change. And this, of course, includes their contribution to sea level rise, hence the theme of this overall seminar series that you all have going on now. Now, the dynamic response of the glaciers, something that I'm very interested in, is really a key component of understanding how glaciers and ice sheets respond to changes in climate, and how they'll contribute to sea level rise and so forth. And that dynamic response depends on a whole variety of factors. So broadly speaking, though, we'll lump a number of these things into two very broad categories. One is the rheology of the ice, thinking about this from brittle through viscous regimes. Today, we're going to focus primarily on viscous regimes, but of course, ice can also be brittle, calve off icebergs, and so forth. And so we are interested in thinking about what that transition is from viscous flow of ice to the brittle fracture and so forth. But today, we're going to focus exclusively on the viscous regime flow. And then we also, as a group, as you mentioned before, think about the mechanics of the bed. So the boundary condition at the bed, and thinking about how the drag at the bed, for example, is related to the rate of slip across the bed, water pressure, and a variety of other factors. So today, though, sticking with the rheology of the ice. Now, rheology is central to everything that we do in glacier dynamics, of course. It underscores much of, or basically every problem that we think about in glacier dynamics, and then it has this broader implication in terms of influencing the uncertainties, or many of the large-scale uncertainties, at least in projections of sea level rise. So I stole this graphic out of the latest IPCC assessment. Lots of people have done this kind of work before, looking at the response of global sea levels to various climate scenarios. What I want to highlight here in the connection to ice rheology is that a lot of this uncertainty, or a lot of these pieces of uncertainty, and particularly things that are described by this storyline, this low likelihood, a high impact, or the deep uncertainty processes and so forth, all these things are underscored by rheology. So rheology comes in, but the rheology of glacier ice comes in and impacts these things in many ways. So On top of this, recent work that has been done suggests that the known uncertainties in ice rheology are actually able to create as much variability in the model outcome as do these climate scenarios. But at the moment, these climate scenarios that are at least put forward by IPCC don't really take into account all of these known uncertainties in rheology. And then beyond that, I would argue that we don't have a particularly good handle on the rheological uncertainties or the related thresholds in these conditions. So ductile brittle transitions, things of this nature, understanding what exactly is the mean and the distribution of various parameters related to the rheology of the ice. So the theme of today is trying to get a little bit of a better handle on this, move toward a world where we can take and actually quantify the uncertainties, the distribution of these uncertainties and the rheological parameters, and use this to drive the next generation of ice flow models, the stochastic models that are coming out. So rheology of glacier ice. So I love this photo. This photo captures very nicely this general sense of the rheology of the ice. You can see, you could look at this and immediately recognize this as being a viscous fluid. So this is what's called a Piedmont glacier. This is specifically the Elephant Foot Glacier in Greenland, but I really like this because it's just a beautiful, almost symmetrical fan shape. And basically what you're seeing here is snow is accumulating up here at high elevation. It's being compacted into glacier ice, and then it's flowing through this notch in the mountain range, and it's spilling out onto this lower lying area. And so you can see even in the simple photo, what is recognizable to us as the flow of a highly viscous fluid, similar to what like syrup would flow across a plate and things of this nature. So glaciers, in essence, of course, are rivers of ice. They're formed by the compaction of snow, which gives them this really interesting polycrystalline structure that's interspersed with air bubbles, it's interspersed with impurities and so forth. So it gives a quite complex flow structure. So it's a really fascinating thing to work with. And so for those of you who kind of think about atmospheric dynamics and ocean dynamics and so forth, turbulence is your kind of bit of interesting complexity. For those of us who live in low Reynolds number space, rheology is kind of our equivalent of turbulence in terms of thinking about the complexity of the material that we're dealing with and the flows that we're dealing with and the parameterizations that have to be made within the model. So broadly speaking, ice is a non-Newtonian viscous fluid. This means viscosity is a function of stress. And that is true, non-Newtonian viscous fluid over time scales longer than about a week, kind of hand waving on that. Right? It's an elastic solid at time scales much shorter than that. And then it'll have properties of both elastic solids and viscous fluids at these intermediate time scales. But for a lot of the problems that we deal with in glaciology, time scales a week, weeks, months, longer, so forth. Viscous fluid is a very good approximation for the rheology of the ice. And the viscosity depends on a whole variety of mechanisms, and these mechanisms that allow for creep. And then these mechanisms are going to be influenced by the temperature of the ice, liquid water content, the grain sizes, that is the size of the ice crystals within the material, damage, that is kind of more macro scale properties of the ice, crevasses and big fractures would be an extreme example of damage, but other features, they kind of break up the continuity of the material at small scales and therefore influence its ability to carry loads and so forth. We can make a long list of things that viscosity depends on. So thinking about specifically the non-Newtonian viscosity of glacier ice, or the rheology of glacier ice, is really a foundational and one of the original topics in glaciology. So the early experimental work provided support by this thing we now know as Glen's law or Glen's flow law. John Glen did a lot of early experiments on this and traced out this power law relationship between the rate of deformation of the ice, or the strain rate of the ice, being a power law relation with the stress, or more specifically the deviatoric stress of the ice, right? We could write this in more general form of constitutive relation for a viscous fluid, where eta here is our dynamic viscosity, and then our dynamic viscosity, depending on stress, raises some power, and then we have this prefactor A up front. In general, this prefactor A is going to be the thing that more or less encapsulates the explicit representation of temperature, liquid water content, and so forth. And N, as we're going to discuss in a little bit, is a thing that kind of encodes the mechanism that gives rise to the creep of the ice, or the viscosity of the ice, and so forth. So typically, the field in general adopts a value of n equals 3, by far the most common value for this particular exponent. So that gives ice this shear thinning viscosity, which just means the viscosity decreases as stress increases, indicated down here. Now, sometimes we'll take things all the way out to the plastic realm, which is the most extreme case, and then occasionally, for simplicity and for some physically justifiable reasons, people will take a Newtonian case for ice. Newtonian viscosity being the easiest one, where we drop out the stress dependence and viscosity just becomes simply a function of temperature and other factors. But n equals 3, by far the most common case, giving the viscosity an explicit relation to stress or deformation rate. Now, there are loads of experiments, and there are sort of a more limited number of field studies that have yielded a range of values for this exponent n, and this is the thing we're going to concentrate on as we go forward in this talk. Broadly speaking, and for the most part, this range can kind of be encapsulated within a range of kind of n equals 2 all the way up to around n equals 5 and so forth. There are arguments for smaller and larger values, but this pretty well encapsulates most of the studies that are out there. So something that is relatively close to Newtonian is something that gets us closer to plastic and so forth. But for the most part, the inferences live in this halfway house between these two extremes of Newtonian versus plastic viscosity. Now, the value of n is really defined by which mechanisms allow for creep, or more technically speaking, it is influenced by the balance of creep mechanisms, which is to say that there are a number of different mechanisms that allow ice to flow as a viscous fluid. All of them are acting all of the time, but the relative importance of each one of these things is going to dictate the value of an exponent if we take something like Glen's flow law, this sort of single element power law relation between deformation rate and stress. Now, most of the mechanisms that give rise to creep can be broadly lumped into these three categories. So we have diffusion creep on one side. What diffusion creep does, it basically allows the void spaces within a crystalline lattice to move or diffuse in response to an applied stress, right? So all materials, particularly all natural materials, in order to get to their minimum energy state, they must necessarily have some void spaces within their crystalline lattice. And so whenever they're deformed, these void spaces will want to move in a couple of different ways. And this movement of the void spaces allows for this macro scale manifestation of viscous flow behavior. So typically, so both by theory and by a little bit of laboratory experiment, we get an exponent of n equals 1 associated with diffusion creep. So a Newtonian viscosity if diffusion creep is the dominant creep mechanism. In the middle here, in terms of intermediate n values, we get n values around 2. There's a little bit of variation depending on some specific details of it, but we get into a creep mechanism known as grain boundary sliding. So this is effectively taking our polycrystalline material that is ice, applying a stress to it, recognizing that there will be stress concentrations down at the micro scale and so forth, and those stress concentrations are going to drive effectively the mobilization of the grain boundaries themselves. So the grains will reshape, orient themselves, and so forth in response to this particular stress. And so there are a couple of different ways in which this sort of thing can happen, but we're going to broadly lump these things together under this term of grain boundary sliding and not worry too much about the details. What's going on in these particular bits. But all of these things, all of these mechanisms that we'll lump together as grain boundary sliding will basically come in at a value of the stress exponent of about n or around 2. And finally, there's dislocation creep. So dislocation creep are just these sort of failed connections within the crystalline lattice structure itself. So these individual water molecules are interacting with one another and so forth, and there will be this missed connection between these two pieces. And so as stress is applied, what happens is connections will be broken and other connections will move over and so forth. And so the dislocations themselves will move through the mechanism and give rise to kind of this macro scale deformation of the ice itself. So these are kind of 1D, effectively, imperfections within the material that are moving along that allow for a pretty efficient means, it turns out, of deformation of the material itself. And so from laboratory studies, we get values of the stress exponent around n equals 4 or so for this dislocation creep mechanism. So as I mentioned before, all of these creep mechanisms are going to be operating all of the time in some manner. But what's really interesting to us, or what's really important to us, is thinking about which ones are dominant. So what is the partitioning of the sort of the total creep, the bulk creep behavior of the material between these different specific creep mechanisms and so forth. And it turns out that ends up being a function of the stress itself, which is kind of an interesting piece of this rheological story, which is to say that the value of the stress exponent is itself a function of stress. So
can I interrupt you for one moment? Sorry, we've got a question in the chat from Vivian. Do you mind if we randomly ask you questions? Is that okay? That was a question from me.
Feel free to, wind migration of voids and lattice also induce crystalline dislocations. So movement of void spaces, the diffusion of void spaces generating dislocations is the question, right? Am I understanding that correctly? To which, the answer is, to my knowledge, at least yes. It would create dislocations, but it doesn't necessarily have to. So diffusion creep can kind of occur. It's somewhat as an isolated mechanism from dislocation creep itself. So quite a different thing. There are various sort of sources and sinks to dislocation creep, which I am by no means an expert in, and so forth. But these are sort of distinct mechanisms, even though they will play together and interact and influence one another at the micro scale. Does that answer the question? I'll let her chime in if not. Yes. So thanks for your question though. But yeah, definitely stop me, interrupt me, holler out a question if you have it as we go along. Talks are a lot more fun when they're more discussion than lecture based. So anyway, getting back to it, so neat thing, stress exponent is a function of stress itself. So as stress increases, we would expect kind of a different partitioning of the total deformation between these different creep mechanisms, which is to say that we would expect sort of different creep mechanisms to be dominant at different states of stress and so forth, and thus give us this different relationship between the stress and the observed rate of deformation. So the takeaway from all this is effectively that we should expect to increase with stress up to, at least according to laboratory studies, up to a value of around n=4, which is dislocation creep up at the highest stresses, or the highest stresses that we would expect to find in most of the terrestrial ice, right? And this, of course, is true all else being equal. There will be a number of different feedbacks and so forth and complexities that come into play in all this. But as a rule of thumb, n increases with stress. And that's basically because dislocation creep becomes increasingly dominant within the material. So n=3, our canonical value, the thing that shows up a lot, is not known to be associated with any specific creep mechanism. So in fact, it's argued, Goldsby and Kolstad made this argument, and a number of others come into it as well, that n=3 arises from some combination of creep mechanisms, or more specifically, a combination of grain boundary sliding as well as dislocation creep. And it happens to manifest in this transitionary region where these two mechanisms are both become important, happens to manifest, at least under laboratory conditions, under the magnitudes of stresses that we would expect to find within the natural system. Right. So this creates this kind of this question about where n=3 comes into play. What should be the proper value of n whenever we're modeling the flow of ice and so forth. Now, for the full range of stresses that are experienced by glaciers, it can certainly be argued that Glen's flow law may be simply too simple, and that a composite flow law is needed. And a composite flow law is quite straightforward in the sense that the total strain rate that we would observe as outside observers through satellite systems and so forth is simply the sum of the contribution of different mechanisms. In this case, I've just written down grain boundary sliding and dislocation creep, because diffusion creep, it turns out, doesn't obviously play a very important role in many of the conditions that we see. So in reality, total strain rate, just a sum of all these features that are going to have different values of n. So listing down 1.8 as a grain boundary sliding mechanism that is at the higher stresses, plus dislocation creep in this case, giving us n=4. So all these things are great, and laboratory studies, of course, are great for controlling different variables, giving us the ability to independently measure stresses and strain rates. But natural glacier ice can have larger grains, and it can have impurities, it can have bubbles, and so on and so forth, things that can't obviously be reproduced in the laboratory. So at the end of the day, we ultimately need to be able to study the rheology of natural glacier ice and to calibrate our parameters and understand what's going on in the models within the natural system itself. Now, of course, we can only do this in areas where strain rate can be measured, typo there, strain rates can be measured and stresses can be approximated independently of one another. Now, a number of these studies have been done, giving an example of a classic one here on the right-hand side by Jezik, Richard Alley, and Bob Thomas. This is from the 1980s, where they looked at the flow of ice shelves, and something that we're going to revisit a study very similar to this in this particular talk. But taking all these studies together to include the Jezik study, we basically get a range of N values, as I mentioned before. Natural glacier ice are going to be somewhere between 2 and 5, so living in this kind of grain boundary sliding to roughly dislocation creep based range of the deformation. N equals 3 is typically argued to be the best fit. Best fit given here kind of in scare quotes, in the sense that it's not obviously truly the best fit to all of the data that we have, but it's a little bit more of a heuristic in terms of the best fit for all the pieces that we have available to us. So we'll talk a little bit more now, kind of going forward about thinking about our approach to testing and calibrating the rheology of the ice. But in a nutshell, what we're going to do is we're going to build on these classic studies like the one from Jezik that we saw in the plot in the previous slide, and we're going to use modern observations to try to advance the calibration that we have and our understanding of the creep mechanisms that are at play in natural glacier ice. So we're going to make inferences from observations of ice shelves in particular. So these are the floating extensions of the ice sheet that we'll pick apart here in a little bit more detail in the coming slides. We're going to use these as our natural laboratories. And we're going to start off by sort of looking at these areas and developing a relatively simple framework. And to do that, we're going to focus on specific areas of the ice sheets that are going to allow us to greatly simplify the problem of calibrating the ice. And we're going to move from there, and we're going to talk about some models that we've been developing for the microphysics of ice to better understand more complex areas, which is to say that the simple framework gives us a really good starting point, but we necessarily have to concentrate on areas of the ice sheet that are sort of less interesting from a dynamical perspective. And we want to develop models to understand a little bit more how we transport those results to portions of the ice sheet that are arguably more important for understanding the dynamics of the ice. And finally, we're going to wrap everything up with a more generalized framework that we're just starting to develop, where we apply machine learning, specifically physics-informed neural networks with variational inference techniques and so forth to constrain the uncertainties. And we're going to do this to infer the rheological properties of the ice and constrain the uncertainties in these parameters. So ice shelves as natural laboratories for studying the rheology of the ice. So quick overview for those of you who are not already super familiar with ice sheets, and particularly Antarctica. So here we have Antarctica. What we're showing in the color map is observations of the surface velocities around Antarctica, noting up here in the bubble that typical ice thicknesses around Antarctica about 1 to 4 kilometers or so. We're going to focus on this talk on the ice shelves that have typical ice thicknesses of several hundred meters. We have the continental United States here, give you a sense of scale, what's going on. But basically, quick description of the view of the data that you're looking at here. So you can see in the color map, logarithmic color map going from yellow to dark, from 30 meters per year to about 3 kilometers or so per year. You notice those fast flowing bits are concentrated into these streaming features. These are fast flowing glaciers and ice streams. And we're going to be particularly interested in this talk on these larger areas of relatively fast flowing ice, because these are the floating ice shelves. I'm talking a little bit about why we care so much about ice shelves for this particular study. But taking them and graying out these ice shelves so it's a little bit clear where these things are and putting them in context for their bathymetry. Again, these are the floating extensions of the ice shelves that come all the way out relatively close to the continental shelf. So these are the areas that we're interested in when we're thinking about connections between the ocean and the ice sheets and so forth, particularly Antarctica, where warm ocean water can come up into contact with the ice shelves themselves. But today we're not going to worry too much about that particular aspect, but rather just concentrate on the ice shelves as our natural laboratories are, the places that we can focus on and study the rheology of the ice. The reason that we're most interested in studying the ice shelves to concentrate on the rheology of the ice is that ice shelves experience negligible drag along their base, right? Because the viscosity of water is much, much less than the viscosity of the ice. And so we can simply neglect the drag along their base, which greatly simplifies our problems in two ways. By eliminating the basal drag, we've eliminated one of the major unknowns that's associated with grounded ice, where drag of the bed is often a dominant component, or certainly not a component that we cannot casually ignore when looking at grounded ice. But over ice shelves, then we're good to go to drop out basal drag. It also allows us to assume that the velocity that we measure at the surface is approximately constant with depth. That simplifies our equations of motion, and it simplifies our observational strategy. So it's pretty easy to observe what's happening at the surface, how fast it's flowing, the elevation of the surface, and so forth. And if we can just assume that the speed of the ice at the surface is relatively constant with depth, then we're in a much better position to be able to estimate the rheology and what's happening at depth and with the rheology of the ice. So we're going to take advantage of, in this approach, this wealth of observational data that we have available to us, in particular the ice velocity that you saw on the previous plot, but this is basically assembled from years and years and years of satellite observations taken from both radar satellites as well as optical satellites that in general are kind of tracking features on the surface of the ice, seeing how these things move along, stacking lots and lots of data sets together, beating down the noise and giving us this beautiful kind of continental scale view of the flow of the ice. It's gotten so good. We have so many observations now. The algorithms are so good that we can get this sort of thing in relatively high spatial resolution with sufficiently high signal to noise ratios that we're actually able to go in and fairly reliable calculate the gradient of this particular field. And it's the gradient of the field that we want, because it's the gradient of the velocity that gives us the strain rate, which is, or the deformation rate, however you want to look at it, which is the thing that we want to know for thinking about the rheology. So that's what we're showing you over here on the right-hand side. In fact, what we're showing is the ratio of the longitudinal strain rate. So this is the long flow strain rate. This is effectively the stretching of the ice in the direction of the velocity vector relative to the effective strain rate, which is the square root of the second invariant of the strain rate tensor. So it's kind of a scalar representation of the full strain rate tensor for the different directions in our coordinate system. So some of these areas will light up. These are areas that, at least on first pass, we can figure are the areas that are dominated primarily by this longitudinal extension of the ice. That is, most of the deformation that we observe is along a particular direction. That's going to be useful for us in just a second as we break these things down. The other piece of data that we're going to focus on are observations of ice thickness. Now, ice thickness is measured typically in different ways over the grounded ice versus over the ice shelves. Over the ice shelves, the way it's typically done, we take very precise measurements of the surface elevation of the ice, usually from radar or laser altimeters. And then we take some estimate of the density, accumulation rates, all these other factors, and get out of it estimates of the ice thickness, of the thickness of the ice, assuming that everything is freeboard. That is, the ice is floating over the ice shelves. And so we're going to concentrate in this particular study on regions of the ice shelves that are sort of effectively free to spread under their own weight. That is, that we're going to concentrate on areas where we can basically make this really important simplifying assumption, where the deviatoric stress in that particular area, the particular region of the ice shelf, can be well approximated as being proportional to the ice thickness, right? And because we can take observations then of ice thickness, we can take observations of the deformation rate from the velocity fields, and these are separate observations. It gives us independent observations of the two components that we want to understand in Glen's flow law. So the effective strain rate, as well as the effective deviatoric stress, as we saw before. And so having these two independent observations of these pieces within the flow law gives us this opportunity to kind of to ask the question of whether or not Glen's flow law is a reasonable approximation to the flow of ice in this area, and then to, if it is, to calibrate the parameters that are associated with it. So again, these are things that people have done before in the past. The advantage that we have at this particular time is that we just have a lot more and better observations than have been available up until the past few years or so. A lot of the older studies were done by actually putting people on the ice, taking survey measurements and so forth, which were naturally limited in space. They naturally didn't give us the ability to kind of do statistics on all of these things, but now we have this full-scale continental view, and so we're able to take a different approach, able to push forward, apply different constraints and so forth. So taking a kind of a general view of one of these particular areas and just highlighting a few areas for the purposes of our discussion today, and thinking about the relationship between the observed strain rate and then the estimated stresses that we get is proportional to the local ice thickness itself. What we find, again, grabbing these general regions that we would argue that our model is applicable and the simplifying assumption is applicable. What we see generally in all of these regions is something that is reasonably approximated as a linear trend between the deformation rate, with the log of the deformation rate and the log of the stresses that are driving that area, which is to say that Glen's flow law, at least in the areas that we're looking at, turns out to be a very good approximation. So there's no obvious need for more complex flow laws that are account for multiple creep mechanisms and so forth. But perhaps more interestingly, the slopes that we get for all of these things give us a value for the stress exponent around n equals 4. So suggesting that the dislocation creep within the ice is a dominant mechanism. Now, those are just particular snapshots of certain areas, but we can go in and we can do some statistics on these things, and we can start to look at the distributions of the estimated values of n, because we have satellite observations kind of around the continent, and because we just have loads and loads of these factors, right? And so that's effectively what we're doing now, zooming in, kind of taking a kernel density approach to try to estimate what the distribution of all these values is. And so what we're showing here is kind of two different lumping together of distributions, or two different ways of kind of representing these distributions. One, you have the general colors circulating around Antarctica. That's kind of rainbow pattern and cyclical pattern that hopefully matches up reasonably well. And two, we have an indicator in terms of the colored outline versus the black outlines. The black outlines are the areas that we're most interested in, because these are the relatively large areas that are better observed, have higher signal noise ratios and so forth. So these are kind of the more important bits to look at in this case. So as we take these pieces and as we apply some statistics to them, just some basic fitting statistics to them, then what we end up with is this clustering of the distributions around pretty much all regions of Antarctica that are reasonably well observed, which is to say that all these things kind of cluster around this a value of 4, or more precisely 4.1, if you will. We get kind of a broad scale uncertainty in the value of n equals 4, plus or minus around 0.4. So a fair bit higher than the n equals 3, the thing that we would typically assume within ice flow models and from this large scale distribution and these new observations that we have. So this conclusion that we come to from kind of stacking together observations, I would say, is part of this sort of broader emerging picture. That is, the conclusion that we make that is around n is around 4 is not new. In fact, it goes all the way back to Glen himself. Yo.
That you ever asked for. The Liberty Tree Pro easily.
Oh. All right. So this is part. This is part of this broader picture. It's a discussion that's been going on in the field a long time. This conclusion that n equals 4 is sort of consistent with many previous studies that have been done in the laboratory and on natural glacier ice. So Goldsby and Kolstad, this is something that we showed before in 2001, sort of compiled a number of different laboratory studies and so forth, and came to this conclusion that kind of n equals 4 at these higher stress regions and so forth, particularly as we get out to dislocation creep. Bonds and others have looked at vertical shear within Greenland in the relatively slow flowing areas, and have fit a different model, still a simple model, but a different model to observational data, and come up with this conclusion that n equals 4. Interestingly, they actually, their data suggests something closer to n equals 4.1, somewhere around that region. And then the Jezik study that I showed before, the original study, they find a range of values, n equals 2.5, I think, if that's right, all the way up to n equals 4.1 is their range of values. They plotted this n equals 3 line. I threw this red line on here, roughly indicating n equals 4. You'll notice that it sort of fits within the error bars and the bounds, sort of arguably just as well as the n equals 3 does, which is something that they report in their particular paper. This study actually, I think, nicely highlights as well the value of the kind of things that we're trying to do with these new satellite observations and so forth, in the sense that we're able to shrink down these error bars, I think, quite a bit. So the error bars that they have on here are large. You notice that they sort of span most of the range of the data. It was definitely the best that people could do at the time. It was a pretty heroic effort to kind of put all these things together. but we can simply do better now as we have this whole host of satellite observations and the ability to kind of stack all these things together. So all of these conclusions that we draw from the work that Joanna was doing are really only obviously applicable to these regions of the ice shelves that are in something that resembles a purely extensional flow, relatively undamaged ice, and so forth. There are a number of caveats that go into these things. I think it's a really important step forward, and I'm glad we were able to do it, but it doesn't sort of fully answer the question in all of the areas that we care about, which is to say that basically we can still ask the question of, do these findings apply to areas of rapid deformation? And so areas of rapid deformation that I would argue are the most important for modeling glacier flow, understanding rates of sea level rise, and so on and so forth. So just as an example, some of the high rates of deformation that we're looking at are the classic example are the shear margins on the ice stream. So this is some work that we did before, and I'll throw it in here just because it makes an okay map for looking at this stuff. So ice streams, the fast flowing bits, Antarctica and Greenland or so forth, are kind of trucking along, roughly speaking. So the trunk of the ice, not a lot of deformation going on within there, but the deformation is really concentrated within these relatively narrow bands. So that's what we're showing down here. So the shear strain rates along the margins of these areas are kind of one of these areas of rapid deformation that we're really interested in understanding the rheology of. We've done some work on this in the past and so forth, but really constraining the rheology of the ice in these areas of high deformation is complicated. It's something that we work a lot on to try to pick apart these various features. And one of the main reasons why it's kind of complex to work on these things is you just have a whole lot of stuff going on that in general is relatively difficult to independently constrain. So we have heating in this area through viscous dissipation. We have dynamic recrystallization because you're doing work on all of these parcels of ice, and so they must necessarily recrystallize and so forth. In response to that, one of the consequences of this dynamic recrystallization would be the development of fabrics that is a crystalline preferred orientation and so forth. So the ice crystals themselves will want to line up and basically effectively act to soften the ice, creates anisotropy and softens the ice in the direction of simple shear that we see in these areas. And then of course, finally, we have relatively high stresses by virtue of the fact that we have high deformation rates in these areas, right? So our existing estimates then do not include these areas of rapid deformation due to these and all these other challenges associated with actually getting at that and sorting out, for example, the difference between changes in the value of N, localized heating, development of fabric, and so forth. These are the challenging things to pick apart given the observations that we have at the moment. But we are working from different angles to try to understand the rheology of the ice in these rapidly deforming areas. So one of the things that we're doing, another student of mine, Megan Ranganathan, has been working on a simple model for ice recrystallization. The basic idea and the way this connects to thinking about ice rheology has to do with the individual creep mechanisms themselves and the dependence of these creep mechanisms on the grain size of the ice, which is to say that most of the creep mechanisms that we talked about before, strain rate, scales, as the inverse of grain size raised to some power, and that power in general is going to be either 1 or greater. And so in general, contributions from individual creep mechanisms we would expect to decrease as grain sizes increase and vice versa. But dislocation creep, the thing that we talked about before that we inferred in Joanna's work that we just discussed with N around 4, a dislocation creep is independent of grain size. And therefore, all else being equal, we might expect that in areas where we infer relatively large grain sizes due to recrystallization, dislocation creep should be the dominant creep mechanism. And in areas where we have relatively small grain sizes, also due to recrystallization processes, then other creep mechanisms are likely to dominate. And so we would end up with a stress exponent of much less than 4. And so then the question kind of lying at the heart of this and thinking about rheology is what might we expect grain sizes to be in areas of rapid deformation? So Megan took this on as part of her PhD work, and she put together and developed a steady state grain size model. And the steady state grain size model basically takes the grain size of the ice as the bulk, average grain size of the ice, takes this as arising from the competition between mechanisms that are going to grow the grains, of course, and mechanisms that are going to reduce the grains. So written over here on the right-hand side, we basically have the sum of two mechanisms that are going to give rise to grain growth. So there's normal grain growth. So there's a tendency of the grains to want to grow to sort of minimize the curvature of the grain itself. That is to say, to minimize the surface energy integrated within a bulk of kind of a broader control volume. And this added to a mechanism of migration recrystallization that we're going to talk about in a little bit. And so this particular mechanism and lumping this in is the novel contribution of the model that Megan put together. And then for grain size reduction, we have this thing referred to as rotation recrystallization. In essence, this is kind of the rheological analog of comminution for those of you who know what that term means. So basically, you're deforming the ice, concentrating stresses in some places. So there would be advantageous for the material to kind of break down, reduce the grain sizes and so forth to allow for the deformation of the ice and minimize the energy state. So migration recrystallization, which is something that Megan added into this particular model, ends up being an important mechanism for understanding the grain sizes within regions of rapid deformation. So the idea behind this is gets back to this idea of dislocation creep. So you have dislocation creep in this reference state lattice, for example, when we start to shear this thing. And then you create these dislocations within the lattice itself. These dislocations will be distributed within the different ice crystals. They're not all going to be. It's not going to be a homogeneous distribution. There's going to be some heterogeneities in the density of dislocations themselves. And these heterogeneities and dislocation density, of course, then are going to drive gradients and stresses and so forth. Because anytime you have a dislocation, you're going to have some strain associated with that dislocation, so some stresses associated around that dislocation. And so since you have a stress gradient due to this gradient in dislocation densities, the material is going to respond to these particular gradients. And so in general, the idea behind a migration recrystallization mechanism then is that the grains can grow themselves in order to alleviate the differences on dislocation densities across the grains themselves. Right. So we take this model, include this mechanism for migration recrystallization. We take the simple model and we benchmark it against the only real data that we have within the ice sheets for looking at the grain sizes, right? So these are taken within the boreholes that are collected in Greenland. This particular one is within the grip ice core in Greenland, which is close to, but not exactly at the summit of the Greenland ice sheet. So this is an area that experiences a little bit of vertical shear, and that vertical shear is going to be concentrated down toward the base of the ice column itself. So we take this simple model for ice recrystallization and we benchmark it against this data. We have one tunable parameter within this model, and we tune it within these ice core data, a number of the ice core data that we have. And we can show that the model does a pretty good job of fitting the data, particularly in portions of the ice core where we would expect the grain sizes to be in steady state. In this area, it's sort of roughly the deeper half of the ice. But what's kind of neat about the model, in particular, at least for our purposes, is the fact that as we get down into the areas where we expect that vertical shear to increase the depth and the vertical deformation to increase, the model does a really nice job of fitting the observed grain sizes within the grip ice core, given the observed temperatures that were collected within the ice itself. And so we get this sharp transition in the model that's associated with a temperature that's getting relatively close to the melting temperature of the ice. And so that's an area where it has been argued and shown in a number of laboratory studies where we get kind of a change in the kinetics of the recrystallization process. We get a change in the activation energy of many of these different mechanisms and so forth. And so migration recrystallization really starts to kick in this area. It gives us this curve over in this region where the ice is getting to be relatively warm. So we would love to have observations within the shear margins themselves to benchmark the model against, but we don't have that. We simply work with what we have, but we'll still take this and argue that vertical shearing is kind of a reasonable analog for the lateral shearing that we would expect within the shear margins of the fast flowing glaciers. So we take this model and we take the benchmarking, and basically we'll run this case. And what I'm showing here is some realizations of the idealized version of this particular model for different observed strain rates and so forth. But the sort of the takeaway message from all this is that for different realistic values of the strain rates that we observe within the shear margins of the glaciers around Antarctica and Greenland and so forth, we'll get various temperature profiles, but more importantly, we'll get different grain size profiles. Interestingly, as we get into these kind of deeper bits of the ice where we'd expect relatively warm ice to exist, warming of the ice through viscous dissipation in this particular case, but as we get down to warmer ice, migration recrystallization really kicks in and takes over and grows the grains. So it gives us a relatively large grain size, or large grain size relative to what we would expect from colder ice or ice that's deforming more slowly and so forth. So yeah, takeaway, the model predicts that the grain sizes will be larger than normal within the shear margins themselves, or shear zones, or pretty much any areas that we would expect to see rapid rates of deformation. And that's because these areas are likely to be within a few degrees of the melting temperature, and that favors migration recrystallization that should give us a net grain growth. Getting back to rheology and thinking about these things, then what does this sort of indicate about what we might expect the stress exponent to be within the shear zones? And so we get in back to this same number that we've been coming to and hovering around before, probably n equals 4 most likely. And the reasoning behind this is simply that rapid deformation implies high stresses, that is higher than those observed within Joanna's study that we talked about before, and inferring n equals 4. And so by laboratory measurements and so forth, we should, if we were in dislocation creep regime on lower stresses before in the study that Joanna did, and pushing these things out to higher stresses within the shear margin should also favor dislocation creep. And then the grain sizes we would expect to be large relative to the slower deforming areas. And since all of these other creep mechanisms are inversely proportional to grain size raised to some power, we should expect that as the grain sizes get larger, the contribution of these different creep mechanisms should decrease. But since dislocation creep is independent of grain size, then it should sort of stay relatively unaffected by these particular changes. And so all these things kind of favor the dominance of dislocation creep within the shear margins. And since laboratory studies have found dislocation creep to be around n equals 4, then we would surmise from that that n equals 4 should be a reasonable first guess within the shear margins themselves. But we got to do more to do these things, and we got to be able to come up with a more robust way to use observations to our advantage in order to infer the stress exponent, the prefactor in Glen's flow law, test rheology, eventually get to the point where we can do pick out models and do a better job of testing models for rheology and so forth. So we're in the very nascent stages of doing this kind of thing. This is work that's led by Brian Rheel, who's a research scientist in my group at MIT. So what Brian's done is he's starting to put together a framework that's built around physics-informed neural networks. And so that basically just means that we're taking into account the physics that we understand about the flow of the ice, for example, that our momentum equations simplify down to the Stokes equations, which is just Navier-Stokes without the inertial term. We can take those things, we can apply it, and we can basically construct a model and do an inference where we require our model predictions to both satisfy the equations of motion as well as satisfy and minimize the misfit with the surface observations themselves. So we take these pieces of something that Brian and others developed in a paper that came out just in the last few weeks and so forth, that's looking at how to predict time-dependent drag at the bed of the glaciers, but using that same basic physics-informed neural network and taking it forward and starting to think about how to apply it to ice rheology itself. And then adding in this new feature of variational inference. Variational inference, effectively, at least as I understand it, is basically just using neural networks, very efficient neural networks, to kind of approximate an MC-MC method, a Markov chain Monte Carlo method for sampling the distribution and so forth. So an efficient way of doing the inference for rheology, as well as constraining the uncertainties associated with those inferences on the back end. Within this framework, we're going to make use of time-dependent observations, in particular, some work that we've done before in trying to constrain the tidal variability of ice flow and so forth, which is to say the tidally driven changes in things like the strain rate of the ice and so forth. That gives us a kind of a new ability, a unique way to push forward and be able to separate out all these different components of the rheological factor. So I'm not going to talk too much about this work because it's all brand new and we're getting to the end of our time. But basically, the synthetic tests that we've done on this show a real potential for inferring the stress exponent N, as well as the prefactor in Glen's flow law, and providing quantified uncertainties associated with these things that are informed by the uncertainties in the observations themselves, and some other ways of constraining the uncertainties related to the simplification of the physical model that we use to make these inferences and so forth. So our goal at the end of all of this in the next few years is to have a very efficient computational framework that takes in this whole wealth of observational data that we have available to us now. It's coming down from satellites, that takes those observations, takes the formal uncertainties associated with those observations, and does the inference for the rheology of the ice, and spits out estimates of the parameter for the ice, as well as the distribution of uncertainties associated with those inferences for the rheology of the ice. So our hopes, of course, is that this sort of thing will be effectively immediately useful then to plug in not only the mean values, but also the distribution of these inferred rheological parameters, and go into things like stochastic models like Liz talked about last week in this particular session and so forth, and do a better job of being able to project sea level rise going forward, and to be able to quantify a little bit better the uncertainties associated with sea level rise, in addition to highlighting a little bit more robustly the mechanisms that are responsible for the deformation of the ice itself. So this is just a quick highlight. I'll point out within our synthetic tests, these things are working within at least a simple framework. That is to say that this particular method is being developed recovers the true value of N within these synthetic tests that have errors associated with them and so forth. So happy to talk with you offline if you have any questions about this. So main takeaway from all this, though, as more data become available, our observations get better, our constraints on time dependence of velocity in particular gets a whole lot better, and our knowledge of the mechanisms that govern ice rheology and our calibration of the related parameters of ice rheology are bound to improve rapidly within the next few years. So I'll wrap everything up. We're pretty much at the end of the time. So what I tried to give you is an overview of recent efforts taking place within my group to understand and better constrain the rheology of glacier ice using the wealth of data that are now available to us from a variety of satellite platforms. So multiple lines of evidence that we presented here and that have been published in the literature, particularly in the last few years, point to a stress exponent for the rheology of glacier ice of around 4, with, at least in Joanna's work, a surprisingly narrow distribution in these particular areas, and especially that is the extensional regions extensional and relatively undamaged regions of the ice shelves. Right, and this all likely indicates a dislocation creep is the dominant creep mechanism that allows the ice to flow as a viscous fluid. Right, and this higher value of N then implies that the viscosity of the ice is more sensitive to changes in stress that current models that typically use N equals 3 allow. So efforts are underway to try to quantify the sensitivity of sea level rise projections to different values of the stress exponent. Not a lot of this work has been done, but there's a lot more interest being generated in thinking about these rheological uncertainties and understanding how they feed into projections of sea level rise. But these efforts to test, calibrate, constrain uncertainties in rheology, I'd argue, should be useful for projections of sea level rise in the near term, as the implementation within existing ice flow models should be relatively straightforward, which is to say that all ice flow models have to have some constitutive relation associated with them. They already have these parameters built in. So making this transition to sort of different values, improving the calibration as we go forward, should be easy to just plug right in to the existing frameworks that we have. And all these things, these calibrations, our ability to test these underlying assumptions that have existed in the field and so forth, they're just going to get better as more data are collected from a growing number of satellites as we move forward. So that is it. That's all I have for you. So thanks for listening. All right, I see Gavin has a question.
Yes, can I just say one moment? Thanks so much, Brent. If you have a question, please feel free to raise your hand or say something in the chat. Gavin just posted a question in the chat. Sorry to interrupt you, Brent.
No, that's all right. Yeah, it's good. I'll just read Gavin's question, unless Gavin, you want to unmute and ask it yourself. So it's a good question, kind of central to the whole thing. If we take a standard dynamic ice flow model and plug in n equals 4.1, what will we see relative to the projections that we see now, faster or slower mass loss? The short answer is I don't know. My intuition is that we would see that the ice sheets are more sensitive to changes in climate, so pumping of warm circumpolar deep water and so forth, than what the current models allow. However, it's not 100% clear that that should necessarily be the case, simply because the ice sheets are always going to be mass limited and so forth. And so if we plug in something and we have a viscosity that's more sensitive to changes in stress that can occur through changes in ice shelf budgeting, calving of icebergs and so forth, that doesn't necessarily imply that particular mechanism should necessarily lead to higher rates of sea level rise projections and so forth. But my intuition would be that we are, with a higher value of n, I would guess that we are more likely to see sort of higher end projections than, or higher end projections becoming more likely relative to n equals 3. But I could easily be wrong about that, given the complexities of how the rheology sort of feeds into this entire model structure. But nobody's done this study just yet.
Kevin, do we have any other questions from the group?
Olga.
Hey, Brent, great talk, but actually you confused me quite a bit between the first and the second part. So you started saying that n equals 4, again, sorry, bells on the background, so it's not. You started saying that n equals 4, larger n is associated with higher stresses.
Mm-hmm.
So my naive understanding that ice shelves are areas with the lowest stresses in general.
Mm-hmm.
And you're coming up with n equals 4 on ice shelves.
Mm-hmm.
Then you say, all right, let's take a look at shear margins where stress is, again, like I would naively believe the highest on ice streams. And
Mm-hmm.
again, come again with n equals 4. So like, how do I reconcile the fact that higher n corresponds to higher stresses, but you just showed that on ice shelves n equals 4?
For sure. Yeah, so that's a great question. Thanks, Olga. So here we go. So basically the argument is that we infer n equals 4, which is associated with dislocation creep, and in the extensional areas of the ice shelves, which Olga correctly sort of points out, have stresses that are low relative to the shear margins themselves. So at least if we believe the Goldsby and Kolstad style model, and once we're into kind of the stresses that are sufficiently high to give dislocation creep as the dominant mechanism, there's no sort of known mechanism until we get all the way out to failure of the ice that would necessarily take over after that, which is to say that if dislocation creep is dominant at the relatively low stresses that we would expect within the extensional regions of the ice shelf, then it's logical to conclude that it should, all else being equal, it would likely be dominant in the higher stress regimes that we would see within the shear margins of the ice stream itself. Right? Does that make sense?
Not really.
Why not?
Well, again, because on ice shelves, pretty much it is just an advection. It's very little deformation. You more or less just advect stuff, right? And in shear margins, you do deform heavily. So effectively, you come up with exactly the same value of n, regardless how you deform. That's kind of what I'm confused.
I mean, there is deformation happening on the ice shelves. I mean, that's how, of course, how we're inferring what the rheology is. Obviously, in a purely advective case, there's no information about rheology.
you're balancing the driving stress and the divergence of the longitudinal stress.
Sure. Yep.
Yeah. So in fact, and the driving stress, which also my second question is, it depends on the density.
Sure. Yep.
And on ice thickness. So depending what numbers you plug into those,
Yeah.
your driving stress can be different.
For sure. Yeah. Yeah. And so we have some, I didn't talk about it in this particular talk to avoid details, but yeah, we have some exploration of a range of different values of densities that would be reasonable for these things. And so their conclusion more or less remains the same, so long as we stick within kind of the viable range of mass densities for the ice. But yeah, you're definitely right. It is dependent on these things. I mean, the longitudinal stresses, so the deviatoric component of the stresses, of course, is gonna scale in the purely extensional regime as being proportional to the local ice thickness itself, right? Of course, we're getting that from the momentum equation. So the gravitational driving stress and all that is built in here, and that's how we get these particular pieces. And so the ice thickness, the estimates of the ice thickness that we have, of course, are a function of the mass density itself, because we're not measuring ice thickness directly in general over the ice shelves. We're measuring the surface elevation and then estimating the thickness based on some estimates of the density. But in addition to this sort of constant of proportionality here contains the mass density of the ice. And so we got to look at those different pieces. We did not go in and redo all of the estimates of ice thickness to look at the full range of the sensitivity of this whole estimate to changes within the density, but we do vary the density and look at these outcomes. And so we get basically a picture that looks very much like this for reasonable estimates of the mass density of ice.
Yeah, but I'm still confused in terms of the mechanism that gives you n equals 4 on both shear margins and the ice shelves, because in my kind of view, the deformation, the method of deformation, and again, I don't know much about grain growth and all those microscopic details, but my sense would say is that the form or the mechanism of deformation is quite different. I don't know, quite slightly or something on ice shelves and in shear margins.
So you're basically, if I understand your argument correctly, you're saying that let's just cast this in a laboratory framework, just to make sure that I understand your question. If I take a specimen of ice within the laboratory and I apply sort of a uniaxial extension to this,
it would be like ice
conditions, that I would get I might see one type of dominant creep mechanism, whereas if I took that same specimen of ice and I applied a simple shear to it, I might see a different manifestation of kind of the balance of creep mechanisms. That's your argument, right?
Yeah, I would think so. Again, I can be easily wrong because I've never done such things. And yeah, so that's but effectively, you got it right. Yeah, that's my argument.
Yeah, I mean, I guess my intuition is the opposite, which is to say that it's not obvious why the sort of the simple shear versus effectively the pure shear of the uniaxial extension would necessarily lead to different creep mechanisms. But I'm happy to talk with you offline about this. But yeah, but you're kind of hitting to you are getting at a key point to all this, which is to say that what we're showing here on the slide right now, what Joanna's doing is a direct inference of what we expect the stress exponent to be from observations, whereas the argument that n may very well be 4 within the shear margins is much more a heuristic argument. It says that assuming that there aren't these kind of wild differences in dislocation mechanisms between the extensional regime versus the shear regime, and assuming that we can believe the laboratory studies and so forth, then we might expect then n equals 4 given all of these other conditions. That's the argument, but we don't have a direct inference of what the stress exponent is in the shear zones right now. It's too hard. There are too many unknowns that we can't constrain with the current observations. So you raise a really good point. Yeah.
Thanks. Thank you.
Yep.
Thanks, Olga. That was a fascinating. Do we have any other questions from the group?
I'm happy to take questions offline as well, but I'm gonna have to run in just a couple minutes.
Can I ask you perhaps something that I misunderstood about the neural network component? So the neural network, was that optimizing for the work of your, I think one of your, I think it was a postdoc working on, yeah. I'm not sure if I understood this correctly. Was that optimizing for essentially tuning parameters, or was it also adjusting perhaps some of the physics? So I think you're sort of fitting a model to observations essentially.
Yeah. So this is tuning for, in this particular case, basically what we're working on is tuning directly for the prefactor. So actually what we're tuning for effectively is the coefficient of viscosity, given all these different, given all the observations and the model for ice flow and so forth. The way we get to kind of an estimate of the stress exponent at the moment is prescribing a stress exponent, tuning in the prefactor within the constitutive relation, looking at the mean square error in this particular case between, in this case, the basal drag versus all these other bits, knowing that the basal drag should be very close to 0 within the ice shelf. So we're using that as the optimization parameter, effectively, if you will, and then changing different values of n. So you can see the discrete points here, and looking at the value of n, that kind of gives us the lowest, the best optimization fit for our prefactor to the observations as we go forward, right? So it's there's kind of a two-stage process at the moment, at least. We're very much in work on this. This is brand new stuff within the past couple months. So we're still sort of tuning these methods and trying to find the best way forward. But that's our current framework.
Thank you. It's very neat.
I think kind of the big part about this particular piece of work is as well as bringing in the variational inference component so that we could actually try to do uncertainties and get a distribution for our inferred parameters or our optimized parameter in a computationally efficient way. So having the uncertainties is nice. And that's kind of our goal going forward with this. But still very much in the development phase. And if you have technical questions about the neural networks and so forth, Brian is the person to reach out to and ask about that, because I'm learning from him.
Thank you.
Yep.
We are sort of about coming up on 15 minutes past now. We did start a little late. That was probably my fault. Sorry. But yeah, thank you ever so much again for presenting for us today. I really look forward to adding this to the YouTube group. And yeah, thanks again. And if you can think of anyone who you think might be neat to give a talk, please let us know. Perhaps we should ask Brian.
Yeah, I'm sure Brian would be down for that. So yeah, definitely. I'll shoot you an email. So thanks for organizing all this. It's a really nice opportunity. So, and thanks everybody for coming.
Thanks everyone. We hope you have a great rest of the day.
See you.
Bye.